Welcome to the nature of matter. So at the end of the 19th century, matter and energy were thought to be distinct. They were thought to be very distinct, very different sorts of things. Matter was thought to consist of particles. Particles had a mass and a position in space that could be specified. Energy, in the form of light, was treated as a wave. Now, waves were massless and they were delocalized, which means we couldn't specify their position in space. But we started to see some problems as we looked at energy and matter more closely. So first was a problem called the ultraviolet catastrophe. So remember that ultraviolet is higher in energy than visible, but higher energy means lower wavelengths. So down here we have the wavelength plotted, and here we see the intensity. So this is a graph showing how much light we get off at various wavelengths, and each curve here is a different temperature. Now remember, as we increase the temperature, the wavelength of light that's at the maximum, the most light that we get out, goes to higher energy, lower wavelengths. So it's going to be shifting to the left. And that's what we see, right? As we move from 3,000 Kelvin to 4,000, that peak shifts to the left. As we go from 4 to 5, the peak shifts to the left, and so on. So, but what happens here, you notice, is that we get to a maximum, and then it drops back down to 0. We get to a maximum here, and it drops back down to 0. Now, this part of the curve, the part on this side, this increase here, that part can be modeled very well mathematically. And there was a very good reason for why it has this shape. What happens is that as you increase the energy, more and more energy is able to be given off at that wavelength. Now this is great, except that mathematically this should just keep going. That should just keep going up and up forever. Which means that at any temperature, you should be just getting a huge amount of gamma radiation, X-ray light. But that's not what we see. There's this maximum here. There's something that's causing this to come back down. And mathematically, we couldn't show why it didn't just keep going up and up. And this was called the ultraviolet catastrophe, because once we get to about the ultraviolet, there's this catastrophic difference between what we actually see in real life with experiments and what our mathematics says we should get. And this was very difficult to explain. And this is one of the problems that came about by assuming that light acted solely like a wave. If light acts solely like a wave, then we should get this red curve. We should get out huge amounts of X-ray light, even at 5,000 or 6,000 Kelvin. But that's not what we see. If we heat up an object to 5,000 or 6,000 Kelvin, we don't see very much of that really high energy light. And so it's not until about 1900 when Max Planck studies this black body radiation and is able to explain the ultraviolet catastrophe only by assuming that light is quantized. So, by quantized here, what we mean is that there are packets of energy. We can't get portions of light at any particular wavelength. We have to get some amount. We get this much energy. And if we move up to a higher energy, we have to get more energy out. So we get quantized, specialized quanta, fixed amounts, fixed quantities of light, of energy coming out of our radiator, our black body emitter. So Planck is able to show that the change in energy, delta E, of a system emitting energy must be in whole number multiples of the quantity h nu. So h is now called Planck's constant. It has a value of 6.626 times 10 to the minus 34 joule seconds, and nu was the frequency of light. So the change in energy of light has to be some number, n, times h times nu. That n has to be a whole number. So when we get light out of a specific frequency, we have to get 1 or 2 or 3 or 4 and so on quanta of that light. We can't get 1.5 quanta of that light to come out. It's got to be a whole number. So each of these packets was called a quantum, or quanta for plural. But Planck isn't able to explain why that's true. Why does that happen? So it's not until 1905 when Einstein publishes his paper that ultimately won him the Nobel Prize. Einstein explains the photoelectric effect by proposing that light itself is quantized. Now, the photoelectric effect is what happens when you take some object, usually a metal, and you shine light on it. If that light has high enough energy, you get electrons to come out of the surface. But it only happens if that light is high enough in energy. And the only way to explain this is if light is quantized. So light can be viewed as a stream of particles called photons. Because if each photon doesn't have enough energy to kick an electron out of the surface, then no electrons come out. Now, after that much energy, if you have at least that much energy, then electrons come out, but you still only get out 1 electron for 1 photon going in. And so, what we're able to see then is that the energy of a photon, so the energy of a photon, E photon, is equal to h times nu. So h again was Planck constant. So this is where Planck's equation is coming from. So the change in energy is equal to some number times h nu. Well, h nu is the energy of each photon. So if you have 1 photon coming out, then you get a change of 1 photon's worth. If you have 2 photons coming out, then you get a change of 2 photons worth, and so on. So each photon has some specific energy associated with it for each specific wavelength. Now, if we want, we can convert that from from frequency into wavelength. So the energy of the photon is h Planck's constant times c, the speed of light, divided by lambda, the wavelength. And this now gets us to wave-particle duality. So if light is acting like a wave, in that it has a frequency and a wavelength, but it also acts like a particle because it has to come in specifically sized packets. It's acting like a particle in that it has to come in specific packets, but it's acting like a wave in that it has a wavelength and a frequency. So light has both wave-like properties and particle-like properties. So this is called wave-particle duality. It acts, depending on how we're looking at it, it acts like a wave or like a particle. And this is also called sometimes the dual nature of light. So if you look at this sort of graphic, you can read this either as light is a particle or light is a wave, because it's both. Light is both a particle and a wave, which is sort of a strange kind of thing to be thinking of, because the things that we see, the objects that we see and interact with in our lives, don't act like both particles and waves as far as we can tell. A basketball acts like a particle, not a wave. And waves on the surface of a pond act like waves, not like particles. But light is acting like a combination of the two. So later, another scientist named Louis de Broglie shows that all particles can also be treated as waves. So even something like a proton or an electron has both particle-like and wave-like behavior. So even that basketball, it has some wave-like behavior. Now, we can't measure it because its wavelength is really, really, really short. So we can't measure it. We can't observe any differences that arise because of the wave-like nature. So De Broglie proposes his de Broglie wavelength. So this is the wavelength of any particle is inversely proportional to its mass and velocity. So the wavelength, the de Broglie wavelength, lambda, is equal to h Planck's constant divided by the mass times the frequency, or rather the velocity. So the faster a particle is moving, the higher v gets, the lower the wavelength gets. Likewise, the higher the mass of the object is, the lower the wavelength gets. So if we have something the size of a basketball, that has a huge mass compared to something like an electron, so the wavelength is ridiculously tiny. And something like a proton has a much larger mass than an electron. So a proton, moving the same speed as an electron, would have a much lower wavelength. So it's very difficult for us to see wave properties of even something like a proton. An electron we can see the wave-like properties of. A photon we can easily see the wave-like properties of. So energy in the form of light is no longer distinct from matter. Now we have matter acting like a particle and like a wave, and now we have energy in the form of light acting like a wave and also a particle. So now energy and matter are tied. There's not any longer this fundamental difference between the two. And then later, Einstein comes along and he gets his famous equation E equals mc squared, showing that energy is proportional to the mass times the speed of light squared. So that's the rest mass, or the object at rest, has some amount of energy that's equal to its mass times the speed of light squared. So now we've linked this concept of matter, with mass, to energy in the form of light, which is massless. So that was the nature of matter.